All right, so what we're doing today is we're going to try to incorporate some equilibrium concepts into our stoichiometry, our mole and particle concepts, our analytical chemistry here. We're going to see where we've come from in redox and show you where we're headed. It's not in redox, but I want to incorporate this idea of equilibrium into our math, our particle and mole theory. So I think the best way to show you why I teach you a lot of concepts at once is to show you a real past AP problem that always does that. I know you guys are uncomfortable when I give you the full bucket of concepts all at once, but I'm hoping you're seeing that it should be making more sense as the year goes on. Any case, so let's start. All right, be crazy and start in order. So what we have is a tall, stylish chemistry teacher. Obviously that's not me, so I don't know who that is. The tall part I got down. The stylish I'm still working on. All right. Any case, the teacher has access to the following three reagents. Okay, now the key here is this. The key here is that the teacher wants to prepare BR2. So what does that statement mean if I'm preparing BR2? That means I'm going to produce BR2. Hey, it's a product, right? We have reactants become products. So right away, I'm telling you that I want BR in my product. So I want to produce BR squared. And here are all the possible half reactions, because it's a redox reaction, right here. And since I want to prepare and produce BR2, which half reaction do I definitely need? The first one, yeah. And because I want to produce BR2, not use it up, I got to do what with it? I got to flip it around. So I do this to remind myself that I flipped it, okay? And I always flip for BR2, who doesn't? And the first question is, find the overall reaction. Okay? So I'm going to write half reaction. So the first one I'm going to flip this reaction. I'm going to take 2Br negative, arrow, going in reverse, becomes Br2 plus 2 electrons. Feel like we've done this before. Yeah, a lot, okay? Just showing you where we've come from and where we're going. It's always good to see that, okay? Now, the question states they want to produce BR2. We know it's a redox reaction. We knew these are standard reduction potentials. And if we're going to make BR2, it's got to be spontaneous, so what must my voltage be of the entire reaction? Positive or negative? Positive. Volts that are positive means they're spontaneous, there's a pathway. Okay, so if this is going to go opposite and oxidize, one of these two have to be as written and reduce. So party people, I need one of these two half reactions. But which one of these two half reactions, when added to the other one that we flipped, gives me a positive? Yes?
The second one?
The second one. Because this is a positive 0.136, because as written, it's really good at pulling electrons. And that's going to be enough to overcome this negative. It's good going this way. It's not very good going the opposite. It's going to be a negative when I flip it. So this positive will be enough to overcome. If you notice, if I pick this one, this is going to be a 0.53 and a negative 1.07. This is just not a strong enough oxidizing agent to force that happen. So we've been through this. It's nothing new. So we write the second one as written because it's reducing. Cl2 plus 2 electrons gives me 2Cl negative. And as we've done a million times before, we make sure that our electrons are balanced. An overall reaction does not ever going to give me electrons. And since there's 2 electrons being absorbed and 2 being produced, they cancel nicely. I don't have to multiply through. And when I balance my electrons, I automatically balance my reaction. This is nothing new. Add everything together and cancel if you can. There's nothing really to cancel. And here's my overall. And by the way, that was a past AP problem. Sometimes they give you a point for the right products and reactants, and that should be 2Cl negative. And if you notice, there's negative 2 on this side, negative 2 on this side, but more importantly, 2 Cl's Two CLs, two BRs, two BRs. Law of conservation of mass and charge, by the way, is upheld. Okay, what's the E0 of cell? Well, we know that the BR2 was flipped. It's really good at reducing, terrible at oxidizing. So it's going to be negative 1.07. And this, of course, is as written is 1.36. So when you add those two together, or just think in terms of, hey, 1.36 minus 1.07, you get a 9, and you get 0.29, yep. So 0.29 volts, and it's positive. You made sure you picked the reaction that gave me positive volts. Hey, nothing there is new. Just showing you where we've come from. Okay, moving on. Now, this is still part of the same AP problem. Hey, that's great, but you know that Br2 and Cl2 can react to form the compound BrCl? No, I didn't know that. Okay, the compound BrCl can decompose, break down into Br2 and Cl2 as represented by the balance equation below. Okay, party people, this reaction has a double arrow. Christmas. So what does that mean? That means that that reaction reaches equilibrium. Equilibrium means the death of a reaction. I don't know if you remember, okay? Eventually the reaction keeps going and reaches that point where there's no more what? Forward or reverse process, okay? Now what is equilibrium? Equilibrium means that there's no net change of products and reactants, which means the amount of products and the amount of reactants stay constant. There's no preferred pathway, okay? As we remember, we did that. So how do we figure this out? Well, if it reaches equilibrium, we have to figure out what position the equilibrium is. Remember, this was 100% reactants, 100% products, and I keep putting it here. So let me just talk about the problem before I describe what we have to do here. They said a 0.1 mole sample of pure bromine chloride is placed in a previously evacuated rigid 2-liter container. Previously evacuated 2-liter container. What that means is we have some container that has no gas in it. It's a pure vacuum. It's 2-liter, and what we just did is we pumped it with 0.10 moles. 0.100 mole of BrCl. Now how could they do that? Well, they can put that container that's been evacuated as a vacuum, and they could pump in the gas until the grams match 0.1 moles. We can do that. We can find 0.1 moles of that, so it's definitely doable. All right, so we've got the gas as particles filling this area. Now, by the way, party people, I can do a molarity of this gas over liter. Couldn't I do 0.1 over 2 liters? I can get a molarity or a concentration. Remember the brackets? Brackets represent the molarity of BrCl. So understand, we can do it for a solution. We can also do it for a gas. But let's get back to this, okay? So we put 0.10 mole sample of pure bromine BrCl in this previously evacuated empty container. And I have it's a 2-liter container, and it's rigid, which means it's not going to change like a balloon. It's going to stay at a 2-liter volume, okay, at a certain temperature. Eventually, the system reaches equilibrium, as the reaction is telling us. What does that mean? System reaches equilibrium. Okay, let's take a look at this, okay? Let's graph the concentration of the products and reactants. So here is going to be above here in a blue color. I think it's blue. So I have BrCl, brackets. That means molarity. I could do that because it's moles over liters. But it tells me how much Br2 I have. And by the way, it's all the way up to the top because I'm starting out with 0.1 moles. Now, in the reaction, remember I started with what? A previously evacuated, which means there's nothing there. So I have an empty container that I just add BrCl, correct? There is nothing yet when I start the reaction, correct? This is 0 concentration. So down here, at 0, I have the concentration of the Br2 and the concentration of the Cl2 combined. It's 0 when we start, correct? Now what's going to happen as this reaction goes? Well, this is going to decompose to build up some products, correct? But because it can go in the reverse, it's going to go in the reverse too, so it's not going to go to completion. Understand what we have been doing for the last couple of days in limiting reagent are completion reactions. Reactions that would go forward until they run out. That means that the reactions we've been dealing with have been spontaneous, very spontaneous. Reactions that aren't as spontaneous means that there's a reversibility problem. Okay, but we can still do our stoichiometry. Just got to consider this. So I want you to understand what this is about. So we're starting at 100% or 0.1 moles of BrCl and 0 here. What happens to the reaction? Okay, well, as the reaction goes forward, this goes down, doesn't it? Because you're going to use some up to make some of that. It's got to go down. But does it go to 0? Because as this is made, it goes in the reverse a little bit. Okay? But guess what we know? This increases too. Because as this is minus in our box, this gets plus, right? Good. Missing, we make this. But because there's some reversibility, we're going backwards. Now, what is equilibrium? Equilibrium is when the rate of the forward reaction is equal to the rate and speed of the reverse. It's the death of a reaction because it looks like nothing is going on. Case in point, if I draw you a bottle, and this is my fancy bottle with a top on, and I fill it up with water, and I put a person here to observe with a big eyeball. He's looking at that line. If it's capped, the line of water is going to stay constant. Why? Because as fast as some water goes from liquid to a gas and evaporates, there's going to be gas going back into a liquid to condense. Because the rate of evaporation equals the rate of condensation, the amount of water stays constant. It looks like nothing is going on. Okay, I've got this bottle of water, and that line is going to stay there forever unless there's a way for the water to escape in a closed system. That's equilibrium. It's the death of the reaction because there's no preferred pathway. I know there's no preferred pathway because the amount of reactants and products are staying constant. So what happens to these guys? They reach a constant point. And equilibrium is where? Once the amount stay constant. Doesn't mean nothing's happening. We still have some of this becoming this, but as fast as this becomes this, this replaces it. And that's why it stays constant. So we're not at equilibrium until we get to where these guys level off. But here's the point. Once we reach equilibrium, we might have more BrCl than the other gases. They're not going to be 50-50 as I've been writing them in my U diagram. And so we have to consider that. And we consider that with a value called KAQ. And we'll get there. Any case, they want you to write an expression for KAQ. KAQ is a mathematical value that tells me once a reaction reaches equilibrium, who's favored. So watch what we do here. KAQ has a couple of synonyms. Okay? So KAQ is equal to KC or KP. Those are the same aliases. Like I'm known as Mr. Grodsky, okay, in the streets of North Riverhead, I'm G Nice, okay, people know me as G, just kidding, I don't know what that even means, okay. Any case, so what's the formula? Very simple. It's going to be the products, the concentration of the products over the concentration of the reactants, notice the concentrations, all to their stoichiometric coefficient power. Let me explain. It's products over reactants, coefficients become exponents. And here's the important thing. Solids and liquids do not apply. And here's the reasoning. Brackets represents molarity. Can you have a molarity of a liquid? Isn't a molarity of moles of stuff dissolved over liter of volume? Well, if you got a pure liquid, you're not mixed with anything. If you're a gas, you're mixed in the air. You can do it that way. So gases are considered to be solutions, okay? But solutions are either aqueous or gas. We have a molarity. Hey, I got a solution of sodium chloride. I mix sodium chloride into some amount of water. That's a solution. That's got a molarity. Gases have a molarity. So solids and liquids do not have molarity. A pure solid doesn't have a molarity. Volume of what solution? Remember, molarity is moles of stuff dissolved over liter of solution. There's only two things that can be a solution. Okay? It's things that are dissolved in water or things dissolved as a gas. So we don't have solids or liquids. So let's write the formula, okay, for this reaction. So KQ or KC, it's the same thing. Let's go find the products. Oh, there's my products. So the products are concentration of Br2 and the concentration of Cl2. And because the coefficients are 1, right, they go to the first power. I don't have to write that. Products over reactants. Who are my reactants? And what's the coefficient? And notice they're all what? When we write an equilibrium expression, that tells me who's favored once we get to this position. Solids or liquids do not apply. Only gases are aqueous, because only gases are aqueous can have a molarity. So party people, products over reactants. Well, my reactant is BrCl, and because it has a coefficient of 2, we put to the power of 2. I will define this, derive this in the springtime again. We're just using this understanding to help us through a stoichiometry. Okay, so I will teach this from scratch in the springtime. We do thermodynamics, but I'm touching on the concept so that when we go back to it, oh, I kind of remember a little bit of that. I'm always doing that. So that is the formula that gives me a number. Now let's look at this for a second. If I have more products than reactants, isn't this number going to be greater than 1? Absolutely. If I have a completion reaction, burn a piece of paper, take the cellulose, the carbon, and react it with the oxygen to make CO2 and water, we know that's spontaneous. There's no equilibrium. And so therefore, this KQ would be huge, huge. So reactions that go to completion, like we have been doing in class, like the demonstration I did, or the labs we've been doing, completion reactions, their KQs are tremendously high, that are basically approaching infinity. They're not even really equilibrium. They're completion reactions. But this one isn't, because there's what? There's some reversibility here. Okay. Now, let's talk about this. So, after the system reaches equilibrium, which means what? The rate of the forward equals the rate of reverse, and we have constant concentrations. Okay. 42% of the original BrCl has decomposed. They want you to determine the value of KQ. Okay, this sounds like something we haven't done, but we're going to use stoichiometry to help this. We want to know what these values are and plug them in here to get this value and try to work it backwards. So we're going to use our stoich table to solve this problem. It looks like something foreign, but it's not. So I'm going to write the reaction. 2BrCl, 2BrCl goes to what? Br2, it's diatomic, and Cl2. And I'm going to put in our boxes. We're going to do an ice table. Okay, and this is initial, this is a change, and this is the end of the reaction. Now I'm putting a little star here because at the end of this reaction, it's not going to go to completion and run out of a limiting reagent. It's going to go to equilibrium, okay? All right, now let's put the value in. Okay, what do we have? Well, they said 42% of the original BR sample is decomposed. Okay, let's put in the original amount. What they say was, what did I put in this evacuated container? Didn't I put this, and how much went in the evacuated container? 0.1 moles. So that's my starting, that's my initial. So let's put it there. So 0.100 mole. We're cool, no E. Other two are zero. Perfect. They haven't reacted yet. We're starting here, just like we've done before. Okay. Now, they said 42% of the sample has decomposed. Decomposition is just this reaction. So let's go find how much has reacted. That's what they're saying. 42% reacted. Don't we put the reacted here?
Yeah, so you do minus 40.42 on that.
Well, yeah, exactly. But hold on. So let's go find 42% of 0.1. So 0.1 times 0.42 gives you 0.041, correct?
42.
I mean 42. That's what I meant. And it's mole. All I did was find 42% of 0.1. So 0.1 times 0.42 gives you 0.042. Okay, now hold on. That means that got reacted. That decomposed. What's the sign there? Negative. You're losing it, right? It's going forward. That's how much you're losing to make the products. So party people, that's minus. Now, if we're going to lose some of the BR2, we're going to make some of these guys. So these guys have to be what? Positive something. Now, careful. Here's our stoichiometry. For every 2, there's what? What's those numbers in front? 1. So if it's a 2 to 1, if I know that's reactive, remember this is moles. This is how many? There has to be half that for this one. Half of 0.042 is 0.021.
Why wouldn't it still be 2 if you have BR2?
Because it's a particle. 2 of these particles to 1 of these particles. I'm not counting atoms. Remember, we're counting this as a singular unit. There's 1 of these particles, 2 of these particles. Great question. Okay? And of course, what's this? Same number, right? Cool. You guys are getting the stoich down. All right. Now we're going to do some hard math. At equilibrium, or the end of the process, this would be plus 0.021 plus 0. So get my calculator. Right? It's going to be, of course, 0.021, 0.021. And, of course, 0.1 minus 0.042, 0.058. Yeah. That's what remains. Is this the excess chemical? You kind of think of it that way, but the bottom line is this didn't go to completion. This should go to 0 if the KQ was so high and products were so favored, but it wasn't, okay? Only 42%. So this is what's left over. Okay, party people now, they wanted you to solve for the value. Well, we have our what? Formula. Now, careful here. These are concentrations. These are molarities. So these are moles. We should divide it by the volume, which is 2 liters. And that would give a molarity. But listen, since they're all 2 liters, since we're dividing by 2 in all of them, we can just put the moles in. That would cancel out. If you don't trust me, you can do it both ways. Since they're all 2 liters, we're taking those moles and dividing by 2 liters for all of them. You're making them all the same. Exactly. So plug in the moles. Okay? So for BR2 right here, so I'm going to rewrite this here. BR2, what's the value? 0.021. And it's also the same for the other one because it's a 1-to-1. All I'm doing is plugging in the value. 0.021 for BR goes in there. 0.021 goes there. And what goes for the BrCl2? Yeah, 0.058. Now careful. Don't forget what? It's squared. Coefficients become exponents. I will explain that and show you why that is in another part of the course. I just want to use this as we're understanding our ratios. So in my calculator, 0.021, we're going to square that. All right. Divide by parentheses 0.058 squared, close my parentheses, and I get my value of the KEQ constant, 0.131. And there's no units, they all cancel. What does that tell me? My KEQ is 0.31. 0.131. I can do this. What's that tell me? Hey, if my K is 1, these are all 1. They're the same, correct? If I'm less than 1, who's favored? Who's bigger? The reactants. What is the sign and what's the value of KQ if it's bigger than 1? If the reaction went to completion, means that if all my reactants approach 0, and this goes up really a lot, my KQ goes up tremendously. Reactions that go to completion, where you run out of something to get a limiting reagent, KQ is tremendously big. But this is tremendously small. It's small because we don't go to completion, and, okay, who's favored? Who's favored for less than 1? From less than 1, that means that this number down here is bigger, isn't it? The reactants are favored. Look at my drawing. Here's my reactant. We reached equilibrium. I still have my reactants above the what? Products. When KQ is less than 1, think about it. It's less than 1, okay? That means that this number on the denominator is bigger. And what is KQ? Products over reactants. The reactants are bigger at equilibrium, and you can physically see that when you plug in the value. 0.058 is bigger than the 0.021. Okay, what is KQ? It tells me who's favored. I'm a chemist. I want to make a product. I look up the KQ and it says, oh, 0.01. I know that I'm not going to make much product. It's not very favorable. Okay? So these are things that we do. All right, now. So that's the answer. But again, I hope you can see that we're using our stoich to get there. The only difference here is this doesn't go all the way. It goes part of the way. But whatever part of the way it goes, we're still maintaining that ratio. Okay? Just stay with me. We're going to do one more part of the problem, and we'll call it quits on this. We'll pick this up another day. Okay. So here is something that we've done in class. Now we're going to precipitation analysis. Next page. And so here's the problem. A student is given 50 milliliters of volume of a solution of sodium carbonate. Hey, sodium carbonate. That's soluble, group 1 ion, of an unknown concentration. We don't know its concentration. We're going to add, and they said what? Excess calcium nitrate, who's also soluble. We're adding excess to figure this out. And let's just check it out. Hey, sodium is +1. The carbonate ion is -2. You can get that from table F or E. Calcium is +2. That you can get from your reference table. Nitrates are -1. And so both of these are soluble. In table F, nitrates are always soluble. We're stretching a -1 over 4 atoms. Coulombic attractions are so small, water can compete. Same thing here. When you pour these together, when you pour these together, isn't the high negative charge going to find the high positive charge and stick together to make it precipitate? You bet your donkey. Okay, I say donkey because I don't want to say ass, but I meant ass in terms of donkey, right? So, calcium carbonate. What is the phase? Solid. That's your precipitate, just like your lab. This is an AP problem. I didn't write this. I try to give you labs that give you the experiences of things you have to know. Now, for this to work, don't I need free ions? Don't I need free ions to move around in solutions? Don't this has to be soluble? So we write what for soluble solutions? AQ. Aqueous. Aqueous. If I have a molarity of something, that means it's an aqueous solution. And sodium nitrate. That is aqueous too. And that's a lie, right? If you drew the box that I'm asking you to draw, you'd have the solid in the bottom, and you'd have sodium plus and NaO3 minus, and then the excess ions right above it as well. Okay, What's the net ion reaction? Oh, first of all, we balance let's balance this. When we balance these kind of reactions, which are called double replacement and reagents, here we call metathesis, but keep the polyatomic ions together, right? 2 sodiums, 1 sodium. Okay, I can't put a 2 here. I don't put a little 2 here and change the chemical formula. People are still doing that. Guys, what have we done in the last 2-3 labs? Determine the what? Empirical formula. The formulas of these have been determined by independent labs. So we know these based upon the ratios in those labs. You can't just arbitrarily change them. All you're doing is putting numbers in front. So 2 sodiums, I have to throw a 2 here. Okay. That gives me how many nitrates? 2 nitrates. Hey, 2 nitrates. Good. 1 carbonate, 1 carbonate, 1 calcium, 1 calcium, boom. Done. All right? By the way, this nitrate's still -1 here. Sodium's still +1. Carbonate's -2 here and still +2. So the second question, besides balancing, is this a redox reaction? Redox reactions, doesn't the oxidation numbers change? What's our precipitate? Calcium +2 hooking up with carbonate -2. Are the oxidation numbers changing? No. Sodium is still +1 here. It's still +1 here. The nitrate is still -1, -1. There are no oxidation numbers changing. This is not redox. We are not moving electrons. So precipitation reactions are not redox because you're maintaining. Hey, if we had lead chloride, that yellow compound, remember this? We started with lead +2 ions that nitrate delivered, and we had Ki, potassium, and iodine negative. Well, guess what? In here you have lead +2 ions in the salt and iodine negative. We didn't change the charges. All we did was present them to each other so that they could find each other to stick together because of their high attractions. So this is not redox. Okay, why? The oxidation numbers are what? Yeah, oxidation numbers are constant. I'm almost done, party people. All right, now here's a good one. Predict the value of the KQ for this reaction and whether this is a completion reaction. Now think with me for a second. As I keep pouring the excess calcium nitrate, which is delivering what? Think about it. I'm delivering to a beaker calcium +2. What's in the solution? Well, I've got sodium plus already there. And I have what? So as I add extra calcium, these guys lock up into a crystal, don't they? Why do they lock up in a crystal? Because coulombically their charges based on Coulomb's law are so strong that they stick together. In water, water can't compete for those charges. So are these guys going to split apart and go backwards? Is there a possibility of this reaction, notice the arrow going this way, going back? Can these ions just get out of the crystal? No! Once they lock up, they can't go back because water can't compete for the charges. This is very spontaneous. This is a completion reaction, which means this keeps going until we run out of one of the compounds. In precipitation analysis, what this is an example of, we add the excess chemical to make sure that we lock up all the carbonate, which is we're after, just like your lab. This is a completion reaction. The equilibrium value would be what then? If this is going to have tremendous amount of products, what's the KEQ value? Larger, huge, reach infinity. So KEQ is going to equal a number, or a large number, okay? And that large KEQs means completion. So if you ever get a KEQ that's like 1 × 10⁵, ding, 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 it's a completion reaction. And one of your 2 compounds is going to go to 0, correct? We're going to have that. That's what I wanted to give you today. Cool. Hey, What's the net ion reaction? Hey, take out the spectators. Isn't it just calcium plus 2 plus the what? Carbonate ion to make the precipitate. Oh, Christmas, what am I doing? To make the precipitate, calcium carbonate, the chalk. Same gosh darn what? Net ion as our lab. I'm not including sodium because it's still floating around. I'm not including the what? Nitrate, it's still floating around. I'm only including what reacted. It just happened to be 1-to-1. Okay, almost done. Now, this is an actual AP problem. Based on what I just said, we added excess calcium nitrate to precipitate out all the carbonate from the sodium carbonate. Is this an appropriate diagram? Is there something missing? And if there is, what should you draw? There's a solid calcium carbonate. That's the ionic crystal of calcium plus 2 plus CO3 negative 2 plus calcium plus 2. See, it keeps going as a crystal.
Isn't calcium ion?
Exactly, calcium is the excess. Although a lot of calcium gets locked up because it's the excess, to get your point on the AP, you needed to write at least one calcium plus 2 ion. That's not difficult. That's an AP problem. You had to write in the calcium and get that point. Okay, based on everything I've been giving you, that's easy peasy. Real fast, we'll touch on F. Okay, now, the point of this question is to find the concentration of sodium carbonate. We added excess what? Calcium nitrate. Why? So that the calcium hooks up with all the carbonate ions that came from the sodium, right? Now watch. I got the mass of the precipitates collected. We added excess calcium nitrate so that every single calcium or every single carbonate could find at least one calcium and make that crystal. We dried it, collected it, okay, and now we have 0.93 grams. We want to know the moles. The question is, how many moles of sodium carbonate did you have originally? And we dissolved this, sodium is spectating, all the carbonate was in the solution, and all the calcium found it. Well, convert this to what? Moles. Now, in one calcium carbonate, how many carbonates? Good. In one sodium carbonate, how many carbonates? So the moles of the calcium carbonate is the moles of the sodium carbonate. So all you're asking you to do is divide this by 100, the calcium carbonate form mass, and that's the answer. Now, that's exactly what they had to do. And this is exactly what you did in lab. Precipitation analysis. Take out one of the ions. Add excess so that every single one of these precipitates out. Knowing the formula, you do your stoichiometry. Don't fall in love with the idea that's always going to be 1 to 1 to 1 to 1. In this case, there was one carbonate per one of these. You may see this problem where it's not 1 to 1. Just be careful, okay? And I'm going to stop there, okay? All right.